this is Himabindu from the Department of CSIT. So today in this video, I would like to explain how to design a PDA, Pushdown Automata, with acceptance of empty stack acceptability and final state acceptability. So what is the equivalence in between these two designing a pushdown automata? So how to design this pushdown automata with the final state acceptability to empty stack acceptability. At the same time, how we can design the empty stack acceptability of pushdown automata to final state acceptability of pushdown automata. So here there are two types of PDAs that we can design. So we already know that we design a PDA with two things. With what are those in the sense? One is the final state acceptability and empty stack acceptability. So here, coming to the language, so the PDA that accepts by the final state acceptability is, suppose here we will derive the pushdown automata is the P, the language accepted by the P, which is the language which we are designing the pushdown automata for that language is denoted by L of P. L is nothing but language of whatever we are designing the pushdown automata, that is a P. So by final state, by final state we have to accept the language. So whatever the given language, we are constructing a pushdown automata, and with that acceptance by the final state. So how to declare this final state acceptability in the sense? This ID is representation. So we already know that the terminology of pushdown automatas, that is nothing but instantaneous descriptions and turnstile notations. So what is meant by this instantaneous description? So this is the instantaneous descriptions are nothing but the transition functions from one state to another state with the top of the stack symbol. So here the three tuple indicates the first one is the current state, and the W is the word which is to be consumed, and Z node is the initial stack symbol. So top of the stack symbol. So this is the moves, multiple moves from one state to another state, all combined together we will write as turnstile star. And this Q is the next state which belongs to the final state. So here we are talking about the final state acceptability, the string which is finally after all the moves in the instantaneous description after reaching the final state. So the state Q is the final state. So and with the empty symbol, so top of the stack symbol is A. So here this is about the final state acceptability. And when coming to the empty stack, we already know that empty stack acceptability is also to design a pushdown automata. So this for the same thing, the PDA that accept the empty stack acceptability. And one more question, we have to checklist. We have to take the checklist in the final state acceptability. So whether the input is exhausted, that is nothing but we consumed the entire W or not. Suppose the W is nothing but 1010. This is the example. So in this one we have to consume all the ones and zeros. So that is we have to check in this final state acceptability, input exhausted. And next, in a final state, so here finally it is reaching the final state or not, we have to check. These are the two checklists we have to follow for the final state acceptability. And coming to the empty stack acceptability, the PDA that accepts by the empty stack. So here the same definition, but the difference in this one is the language is, so here the language accepted by the P is denoted by N of P. So here N is nothing but empty stack. Empty stack. To differentiate between the final state and empty stack, we are writing N symbol of P and N of P by, and empty stack is, so W, the string W, and this ID instantaneous description we already discussed those. First Q naught is the initial state, and W is the word which is word or string which is consumed, which is to be consumed by the pushdown automata, and Z naught is the initial state, initial stack symbol. And next, these are the turnstile moves. So multiple moves are there. So here we'll represent the multiple moves with the star representation, turnstile star. And Q, so Q is the last state, so which is belongs to. So now here the Q, we are not saying that it is only exactly final state. So what the Q is which belongs to Q, capital Q. So capital Q is the set of final state, finite states, not a, it includes the final state and all the states in the pushdown automata. And here the Q, the next state, and the empty symbol epsilon and epsilon. So whenever it is the string, after consuming the string, we are reaching empty stack. So stack contains does not any initial or initial state values also. So the stack should be like this. So whenever it reaching this kind of empty stack, so we can say that it is the pushdown automata is designed by the empty stack acceptability. So here the difference is between here. So here A, and so here the A is nothing but the stack which is having something. So A is having, and here when compared to empty stack acceptability, the stack which does not contain any value. So here this is the difference. So here we can say that we can design a pushdown automata by two design of pushdown automata. One is the final state acceptability and empty stack acceptability. And we have to check the list here with the empty stack acceptability also. So input exhausted or not, we have to check. Is the stack empty? We need to check whether after consuming all the input strings in the pushdown automata, we have to check the after reading the entire input, we are reaching the empty stack or not, we have to check. So these are the checklist followed for the empty stack acceptability. And does PDA that accepts, we can pose one question like, does a PDA that accepts by empty stack? So empty stack need any final state specified in the design? So for this we can answer in the next slide. So here the empty stack which is which needs the final state or not. So here we'll check with the example. So here we can construct, for the same example, we can construct both acceptability, like PDA constructed by the final state acceptability and PDA constructed by the empty stack acceptability. So we'll take first final state acceptability. As we already know that how to design a pushdown automata. So here we are taking all the possibilities. So initially we have to initialize the stack with Z0. So here for when coming to the definition, so PDA definition. So PDA definition is nothing but for the empty stack, final state acceptability. So Q, so which is having Q0 and Q0 and QF, and next input symbols. So here input symbols, there is a example of balanced parenthesis. So parenthesis is nothing but like this. So we have to check the string which is matching this open and end braces or not. So input is equal to open and end brace. And next, so tau symbols. So tau symbols and Z0 is the top of the stack symbol, and Q0 is the initial state, and final state is QF. And what yes, these are the definition of pushdown automata for the balanced parenthesis example. So here for this one, first step what we have to do to construct a pushdown automata, we have to initialize the stack with Z0, we are initializing, and we have to check for this balanced parenthesis. So here whatever the starting brace we are reading in the string, we have to check, we have to move that symbol into the stack. And the logic behind this construction of pushdown automata is whenever the open brace appears, we need to push into the stack. And whenever we are in the string, we are reading the end brace, we have to pop the open brace. So this is the logic behind this one. For this kind of logic, how to construct a pushdown automata. So initially we have to empty string, and with top of the stack symbol is Z naught, we have to move nothing. So top of the stack symbol is Z naught only. So there is no operation here. And next, whenever we see the pushdown, whenever open brace and top of the stack symbol is Z naught, we have to push that one. So push that symbol. So this is the thing what we have. And again, if we have the string like this, so here we consume for this input, we push that symbol into a stack. And for this string, whenever top of the stack symbol is open brace and we have to top input is open brace, what we have to do, we have to push that. So that is here the input symbol and what is the top of the stack symbol, and after pushing that we have the two symbols here. And next, open brace. So here whenever this symbol appears, the closing brace appears in the string, and we have to pop, and top of the stack symbol is open symbol, and we have to pop that. So there is a nothing. So popping, that means that the open whatever there in the top of the stack symbol is popped from the stack. So that is represented with epsilon symbol. And these are the moves. And whenever the top of the stack symbol is a Z naught, and after this one there is nothing, so empty string, and Z naught top of the stack symbol is there, we have to go to the next state, that is a final state. So here this is how we have to construct a pushdown automata for the balanced parenthesis with final state acceptability. So here the final state is there, QF. So QF is nothing but QF or Q1. So whatever there is, it is final state. So now we will construct the same example with the empty stack acceptability. How? So here we have to remove that final state, and we have to add that symbols to the same state only. That is how what we have added. So here the top of the stack symbol is epsilon, and the top of the input string is epsilon, and top of the stack symbol is Z naught. So here we need to pop that Z naught also, and we need to pop, and we have epsilon symbol. So that is nothing but the top of the stack symbol is Z naught, and input string, after reading entire input string, we have only the top of the stack symbol. So here the top of the stack symbol appears, we need to pop that one also, and we need to empty that stack. So this is how we written the instantaneous description, and here the starting state is same. So this is how we can convert the final state acceptability and empty stack acceptability for the same example. And here now we can also check whether the string for this string acceptability will follow, but for these two pushdown automatas. So this open, so well, the logic behind, so open brace appears, so 3 times we need to move that into a, so Z naught. So here 3 times are there, so 3 times are there, so 3 open braces we need to push. And next, and end braces is there, end brace, and for that one we need to pop first one, and end brace, pop the second one, and again we add open brace. So here open brace is there, and next open brace finish, and next closing brace. So closing brace is there, and top of the stack symbol is open brace. What we need to do, we have to pop this one, we finish this one, and next closing brace is there. So closing brace, and top of the, after removing all these symbols, we have only the top of the stack symbol is open brace, and we need to pop that one also. Why? Because the closing brace and top of the stack symbol is open brace, we need to pop that one. So we have Z naught, till now we have Z naught up to this. And then next open brace is there, so we need to push that into the stack, and whenever the closest brace is there, So close brace is there. We need to prop the open brace. So finally we are having the Z0 symbol. So Z0 symbol. So if it is a final state acceptability, so this PDA is accepted, this string is accepted by this pushdown automata. And if we are going for the empty stack acceptability, so in that one, so when after this one, we need one more operation called Z0. So epsilon. So after reading entire thing, we have only epsilon. So epsilon and top of the stack symbol is Z0, and we need to pop the turn also, that is empty stack is there. So here this given input string which is accepted by the both final state and empty stack acceptability. And we have the equivalence of this pushdown automata constructed with the empty stack and final state. So here, what is this equivalency? So here equivalency is nothing but we can convert from one form to another form. So that is final state, we can convert the final state to empty stack and empty stack to final state. So here this is the equivalency of this pushdown automata. And how to convert the one form to another form, we will see. So here the pushdown automata accepted by the final state is given as PF. So PF is nothing but final state. And what are the definitions? So here for the definition of final state, we have the final state F and pushdown automata accepted by the empty stack. So here empty stack is Qn, we are representing a Qn sigma and and tau symbol and transition and Z0 and Q0 and Z0. So there is a no final state. Why? Because it is an empty stack acceptability. Yes. And next theorem. So here we can say that from Pn to Pf we can convert and Pf to Pn. So there is a equivalence in between this, and there exists for every Pn there exists a Pf. So how that is equivalent in the sense language of pushdown automata is equal, pushdown automata of final state is equal to the pushdown automata of empty stack. So same way. So with these theorems, we can prove that both are equivalent to each other. How this theorem will prove? And here we will take the definition and how to construct this empty stack to final state. So here the input is empty stack and we have to convert that into a final state acceptability. So empty stack which is having the which is not having the final state. So all the states within symbol we can represent. So here the final state we have and we have to convert, and here so this is nothing but pushdown automata with the empty stack. So empty stack which is having not final states here, and initially we have, and whenever the Pn stack becomes empty, so make Pf go to a final state without consuming any additional symbol. So here we need to add a final state to the empty stack acceptability. So without consuming any additional symbol. So that is nothing but epsilon symbol. So epsilon we have to give for the final state. So and to detect that empty stack in Pn, PF is nothing but pushdown automata of final state pushes a new stack symbol X0. So instead of Z0, so Z0 is there in the empty stack acceptability. Additionally, we have to convert this empty stack to final state in the sense. So additionally, we need to take X0 symbol and we have to give that initializing with the X0 symbol. First, we need to initialize this X0 and later with the Z0. And for this one, we have to add initial state, that is nothing but P0. So P0 we are initializing with the state name, new state we have to add. For that we have to initialize empty stack, and we are not giving any input string. So we are without consuming any input string, we have to give that new stack symbol. So how to give that in a sense? So here the X0 on top of the stack symbol is X0. So So initially we have to push the x naught into the stack, and after that x naught and next symbol is z naught we have to push. So empty string and top of the stack symbol is x naught is there. We have to push z naught. Z naught we have to push. So this is how what we have done. And finally we have to, in the final state acceptability, we need a final state. So here this symbol, additional symbol. So the here go to final state without consuming any additional symbols. So entire there in the final in non-empty state. So we have to give additional final state to that one, and final state with the empty stack, empty symbol, and x naught, and top of the stack symbol is x naught, and we need to do nothing. So this is how we converted. We have to give additionally a new two states. One is a initial state and final state. So for the final state acceptability, we need a final state, and for that one we need to give additional without consuming any input string. We need to go to the final state. So that is the thing. So after writing all this one, first we will write the definition. So here the PF is nothing but, while converting empty stack acceptability to final state, we have the definition like this. So Qn is nothing but, so this entire states union, these two are the additional symbols. So the P naught and PF are the additional symbols. So we are additionally adding these states to the Qn. And next tau symbol also. Initially we have only z naught and whatever there in the sigma symbols. So sigma, whatever there in the epsilon, we need to add that one. And also we have x naught here. So additionally we are pushing one more stack symbol. So we are adding that tau symbols with the x naught. And transition of a final state, and P naught is the initial state and PF is the final state, and top of the stack symbol is now x naught. So this is how we converted the Pn to PF. That is nothing but empty stack. So this empty stack to final state. So here this is the construction. And example for the same, how to construct with the example. So how to construct a empty stack to final state acceptability. So here we'll take the example of open brace and close brace example, and we already know that. So these are the turnstile these are the IDs. So here open brace is there, we have to push that into the stack. So here the Q, so open brace is there, we have to push that into the Z1. So here Z naught, Z1, and top of the stack symbol, and here the Q naught, the close brace is there, and Z naught we have to, Z1 we have to push. So here we have this same, these balanced parentheses we already know, and this is the empty stack. And here we additionally what we have to do, we need to additionally add to initial state and final state. So for the same thing, how to add the initial state. So this is how we have written. First we have to add the initial state and with the x naught and output. So final state without consuming any input symbol, top of the stack symbol is x naught. We need to move to the PF. And in coming to the transition functions, so here the transition functions, additionally we have two things. So additionally initial state is different here. So for that one, P naught comma epsilon, without consuming symbol, we have to, top of the stack symbol is x naught, we need to push the z naught. So like that we have to add the two additional transitions and two additional states for the converting in empty stack acceptability to final state acceptability. And now one more, we have to convert a final state to empty stack. So final state to empty stack is same, how to construct this one. So main idea of this empty stack to a final state is, whenever the PF reaches a final state, So whenever the PF is nothing but push down automata final state reaches a final state, just make a transition moves into a new state, clear out the stack and accept. So here after reaching the final state, we the main idea mainly after consuming all the input symbol, it is reaching the final state in the final state acceptability. So here after reaching the final state, we have to give additional empty symbol and we have to move that and we have to pop that or whatever there in the stack symbols we have to pop, and we need to empty that stack. So how to do that one, we'll see. To address this, add a new symbol, new start symbol and not tau symbol of PF. Not in the, so here Z0 is there, and instead of this along with the Z0 we have to also add the Q0, X0. So here the additionally we need two states. So here the state, instead of PF we are writing the empty stack. So here empty state we have to take and epsilon symbol and sigma and tau symbol, we need to add the x0, we have x0 to the tau symbols, and transition q transition of delta of n, and p0 is the initial state and x0 is the top of the stack symbol. So here there is a no final states if you observe. So finally we are converting that into an empty stack. So empty stack, there is nothing, there is not having a final state here. And here we are taking this final state. So here double circle, we already know that it represents the final state. So we are converting the final states to empty stack. So here the final states are there. So those final state, first initialize this with the new new state, that is a P0 with epsilon move. So that is epsilon move, and we need to push that x0 into a top of the stack symbol. And next, after all the final states which are reaching one empty state, so with the with the epsilon symbol and any, so whatever there, it should be eliminated. So we have to, whatever there in the stack, whether it is Z0 or X0, whatever there, we need to pop all the things without consuming and reaching the empty state. So here the empty state which is reaching PE. So here without reading any symbol, we have to clear out the stack and accept it. So here what is this meaning in the sense? So anything there we need to pop that one. So that is nothing but clearing out the stack, and here whatever there in the stack, we need to clear all the stack and we need to move to the one state. So that is nothing but empty stack acceptability. So here we converted the given final state acceptability to empty stack acceptability. So this is about the equivalency of pushdown automata, which is acceptability by the final state acceptability and empty stack acceptability. So these are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.